Great.
Can you see?
Yep.
Can you see
So
that?
yeah, I see it. So maybe not the full screen, but yes. So I will probably give you after 40 minutes, like a 10 minutes notice, like leaving 10 minutes of question. So after
Okay.
40 minutes, I give 10 minutes more, and then
Okay.
try to wrap up in 15 minutes, leaving some question. You can probably go over a little bit, given
Okay.
this. Yes. Okay. So take it over, please.
Okay. Thank you very much. I'd like to thank you, the organizers, for inviting me here. So this talk is based on 2 papers in collaboration with Jose Trevisan and Koji Yamaguchi and Takeshi Tomitsuka. Okay. So let's move to the first part, introduction part. As you know, the black hole physics has a very close relation to quantum information. So actually, you have 2 big issues related with quantum information in black hole physics. One of them is, of course, black hole information loss problem, which was proposed by Stephen Hawking in 1976. Let us consider a large black hole in a pure state psi, like that. Then this black hole can emit Hawking radiation and lose its mass, and the black hole is becomes smaller and smaller and smaller. And after the last burst of the black hole, if we have only some radiation in space, then this radiation can be described by a mixed state, a density matrix like that. Okay, but we assume that at initial time, the black hole is in a pure state. So in this sense, this process describes the process which breaks the unitarity in quantum mechanics. Okay, so this is a very, very big issue. And why this problem is so serious? So because we have a type of obstacle, that is release of astrophysical amount of quantum information inside the horizon using small energy of the Planck scale order, that is almost zero energy, as the last burst of the black hole. So this is a very tight, very severe constraint to resolve this problem. Okay. The other big issue is the black hole entropy problem. So here we have a black hole and event horizon. Then, so this black hole has a Bekenstein-Hawking entropy, which is proportional to the horizon area. And here, G is the gravitational constant. And this entropy usually interpreted as the thermal entropy of a black hole. Then the question is the following. What is the statistical mechanical origin of this entropy, especially for non-BPS black hole case? Is it entropy or not? So it is a very interesting problem and has not yet resolved fully. Okay. So this is also a tough obstacle to resolve this problem. That is, no Hare property of classical black hole spacetimes. So usually, so such a spacetime cannot have so many microstates. So we cannot see such a microstate in the classical black hole. So we cannot count the microstate by such a finding a microstate. So this is the issue. Okay.
So sorry, just probably this is not to do with the talk, but I usually have a problem with that argument because even in Schwarzschild, we have a mass that's a continuous parameter.
Yes.
And then if you quantize in quantum mechanics, it's just to become quantized, although exponentially dense. That's it.
Oh, so you mean, anyway, we have 3 here, like energy and charges and angular momentum. And you may mention about the quantization of the mass of energy of the black hole, right? But so
that gives a Bekenstein-Hawking.
Oh, yeah, that's in my opinion. But in my opinion, that's a very naive picture. But I'd like to more make a detailed discussion later.
Oh, yeah, of course. I totally understand. But you said this is a tough obstacle, but it's probably that itself, no hair, zero, and what's the origin of this many thing? That's just the continuum. The same
Yeah,
as, amplitude in harmonic oscillator is now quantized, one half is
yeah,
one
yeah,
half.
yeah, yeah, yeah.
I
Yeah,
think
you're
it's the same phenomenon.
right, you're right. But I just say, so many old people said. So,
Yeah. Okay. Yeah. Okay. All right. Yeah. Okay. Then
so
yeah.
now I'd
We
like,
on the same page. Yes.
yes, I'd like to explain more detailed part of
Sure.
in my, okay?
Yeah. Sure.
Okay. And before going to my idea, so I'd like to explain some scenario proposed by Hawking premise Ranger. So we have one possible scenario to resolve these two problems. So the name is black hole software scenario. The software generated by asymptotic symmetries at horizon. So they propose an interesting symmetry-based conjecture, which may simultaneously resolve the information loss problem and the black hole entropy problem using super translation and super rotation at the black hole horizon, and using Bond-Metzner-Zach symmetry at the near future infinity. It might be interesting, but gravitational vacuum degeneracy with zero energy near horizon at the near future infinity plays a crucial role in their scenario. So this is a recently called software at black holes. Software may preserve whole the quantum information and simultaneously generate horizon microstates of black hole entropy. Possible, so this might be possible resolution of information loss and zeroing the black hole entropy. But I'd like to provide some present status summary of their scenario. So unfortunately, their scenario cannot work about the black hole information loss. So now many people believe that software here on horizon may be too thin to resolve the information loss problem. For the resolution of information loss, the scenario of zero-point fluctuation pattern of Hawking particle remains fascinating in my opinion. But about the black hole entropy problem, please. So, do you have some question? No. Okay. So, in the software scenario, so black hole entropy problem can be resolved because this symmetry can generate microstates, and the number of the microstates can be order of the Bekenstein-Hawking entropy microstate. So it may be still fascinating. And also, I'd like to have a point. I'd like to give you some note. So this is very well-known fact. Infinite mass limit of the black hole horizon is regular horizon if in flat spacetime. So in this sense, the black hole physics can be analyzed and discussed in near flat spacetime. So this is a very interesting point. So here I'd like to provide a first message of this talk. We construct a general theory of gravitational holographic charges on ring graph horizons for 1+3-dimensional linearized gravity field in the Minkowski background. Especially, we give a general formula of a holographic charge shift of super translation and super rotation induced by informing matter absorption. Okay. And also, in order to resolve black hole entropy origin, exploring general asymptotic symmetries at horizon like software is crucial. And actually, we have many papers about such a symmetry. So many papers have already found various symmetries at horizon. But unfortunately, this symmetry list is not complete yet. So we need easy and systematic methods to find asymptotic symmetries at horizon. So I'd like to give you the second message of this talk. In the ordinary scheme, it is a very heavy task to find asymptotic symmetries at boundaries in general relativity. But recently, we provide a simple scheme, that is, covariant building block approach to find asymptotic symmetries at boundaries. By using our formulation, we have found a new software symmetry under Lindlar horizon. The name is superdilatation symmetry. I'd like to explain later. So this is outline of this talk. In the first part, I'd like to explain briefly why we have many microstates at horizon, even in no-fair spacetime. So you may grasp the idea about that. In the second part, I'd like to explain the holographic charge shift at Lindlar horizon. In the third part, I'd like to explain our new formulation, that is, covariant building block approach to asymptotic symmetries at boundaries. And after that, I'd like to summarize my talk. Okay, let's move to the first part. So let us first take a glance at the idea of soft-hair microstates at horizons in no-hair black hole spacetime. Okay, so let us first consider classical black hole geometry. Horizon software of black holes comes from would-be gauge freedom of general covariance and the homomorphism. So this is a similar mechanism of emergence of momentum eigenstates orthogonal to each other. Okay, now let us consider the inertial frame spanned by the coordinate system x, y, t, like that. From this inertial frame, we have a black hole at rest without momentum, with zero value momentum. Okay, and also let us consider another inertial frame like that. This is spanned by x prime, y prime, t prime. Okay, and from the viewpoint of the another inertial frame, this black hole is just running with a non-vanishing momentum p prime. Okay, so but this is just a picture change by using a coordinate transformation. We have no physics at all yet. Okay, but here we can add now physics. The physics is a symmetry. So we must have Lorentz covariance in the theory. Okay, this is the point. Then this symmetry predicts the existence of such a black hole state with non-vanishing momentum in the original inertial frame. Okay, so can you understand this point? So this is just a coordinate transformation, but we assume that the Lorentz invariance we have, then this invariance predicts the existence of such a black hole state. But this black hole state has a non-zero value of momentum. So we have now two states. One is the state with p equals 0. The other state is p equal m sine omega. Okay, so they take a defined value of momentum. So they should be orthogonal to each other. Okay, so we should count independently these states. Okay, and also we can change the parameter omega continuously. So by using this parameter, we can generate an infinite number of physical states with different values of momentum. Okay, even in a single classical black hole geometry. So at first, we have only no-hair black hole geometry, but by using such a symmetry argument, we can predict infinite number of physical states, and we should state counting. We should do state counting by using this state. Okay, this is the point. Now we can apply this argument to near horizon regime. Okay, so software here of black holes comes from would-be gauge freedom of general covariance. Now, let us consider such a classical black hole and horizon, and then we use some coordinate system. Then we would like to consider super translation and super rotation. Okay, super translation is just a time shift depending on the position on the horizon. Super rotation is just a general coordinate transformation on the horizon. Okay. Anyway, we have such a coordinate system, and we can evaluate the charge of super translation and super rotation. Then, this black hole has zero value of the charges, but we can change the coordinate by using this transformation. Then we have such a different state. So this black hole state has a non-vanishing holographic charges about the super translation, the super rotation. Okay, but this is just not a picture change. So we have no physics at all. But here, we must have asymptotic symmetry as a part of general covariance in the theory. So this is the physics. So this symmetry predicts that in the original frame, we have another excited state of a black hole. Okay, in this first coordinate system. So the charges of super translation and the super rotation does not vanish. Okay. Then, in this sense, we have many physical states with different values of the charges. So in state counting, we should discriminate these states to evaluate the entropy. This is the point. So can you understand? If you have a question, please give me. So this is a very crucial point in my talk. Okay, are you okay? Okay, let me go. Okay, contrary to our case, so Hawking-Perry-Strominger software does not work in classical regime because their coordinate system near horizon may be physically implemented by free-falling block-numbered clocks distributed in the space, which play a role of the detector of metric perturbation software here. So the free-fall observer does not see anything due to equivalence principle in GR. Okay. So Hawking-Perry-Strominger finds in the setting stationary black holes do not carry classical super translation here at horizon. This is a very natural and trivial result, in my opinion. But we may have purely quantum software in their scenario, but due to the lack of the computable quantum gravity theory, the exact quantization has not been achieved so far. But recently we have the paper, the Hawking-Perry-Strominger. In this paper, they argue that we may have such a we may perform such a state counting by using a K-shift correspondence. Anyway, contrary to their case, our software here can be observed even in classical regime. This is a very crucial point. In your coordinate system implemented by accelerating block-numbered clocks distributed in the space. So stationary black holes indeed carry non-vanishing classical charges of super translation and super rotation. So this is a big difference from the HPS scenario. Okay. Okay. So this is the first part. Let's move to the second part. So holographic charge shift at linear horizon. Okay, now let us consider near horizon geometry of infinite mass black hole. And then, so this can be described by the linear metric at flat spacetime. Here we have a Minkowski spacetime, and here we have a linear horizon. Then, so asymptotic symmetry near horizon can be analyzed, then we can check that we have super translation and super rotation. So this is a metric, asymptotic metric set. So this is the background metric of linear metric, linear spacetime. This is the perturbative part. And now the linear horizon stays at low equal infinity in this coordinate system. Then, so asymptotic metric near linear horizon is given by this equation. So here, delta is given by this equation, and this is very, very small near horizon. Then we can choose such a form of condition for the metric. Then, so this metric form is invariant under asymptotic symmetries near horizon, super translation and super rotation. Okay, so this is the definition of the transformation. Okay, so due to the asymptotic metric form, so rigid tidal volume charges are indeed integrable. We can check about that. So we can integrate such a charge variation, and we get explicit result about this form. And this part corresponds to super translation. This part corresponds to super rotation. Okay, so we have a non-trivial dependence of such a metric. So in this sense, we have a non-trivial, non-singlet representation of the black hole. So in this sense, we have a microstates of the black hole even in the classical regime. And super translation and super rotation generate excited metrics from the ground set metric, ground set linear metric. So this is background metric, and this super translation, super rotation. Then we have excited metric, this one. So originally, the background metric has the zero charges of super translation to super rotation. But now, for the excited state, we have a non-vanishing value of the holographic charges or super translation to super rotation. Okay. So this is a non-singlet representation as a software here, even in classical regime. Okay.
Excuse me, I have very simple questions. May I ask you?
Sorry?
I have a question. You know, when you apply the super translation, this kind of, so the new metric we generated.
Sorry, your voice is now broken. So could you check your voice? So I cannot see your voice because your voice is broken.
You can hear me now? You can hear me now? You can hear me?
So,
okay, I will keep it for the end of the call.
Okay. Anyway, so later you can ask again. Okay. Okay, so let me start again. Oh, sorry. I lost my position. Here. Okay. So the asymptotic metrics and charges are observed by metric detectors, which consist of accelerating clocks exchanging signals and accumulate metric information. So this is a conceptual picture of such metric detectors. So these clocks distributed slightly outside the horizon. And these clocks exchange a signal. Now, here we have a gravitational field generated by moving matter source, which pass through this horizon. Then we have some perturbative deformation of spacetime. But this information can be implemented to the signal clocks data. So these clock data can reproduce such a metric. What kind of gravitational wave just through this horizon, we can reproduce such an information by using such data in the clocks in the later analysis. Okay, so this is next. I'd like to discuss gauge fixing in a weak gravity field case. Here, this ordinary Minkowski space-time background, and here this perturbative part, and introducing such a conformal linear coordinate system. Then we get this matrix. Then we'd like to use such a specific gauge fixing condition. We call this linear gauge fixing. By using this gauge fixing, these relations also satisfied. And then, in summary, the fall-off condition of the metric is given by these equations near horizons. Okay. Note that this asymptotic metric form is also invariant under supertranslation and superrotation. Simultaneously, the corresponding charge evolved from 0 to non-zero values during the matter passing. So let us consider the charge of supertranslation and superrotation for weak gravity perturbation. So this is a setup. So this is a Minkowski background. We have an informing matter, and this matter has a T mu. This is the energy moment tensor. And this energy moment tensor T mu is the space-time perturbation H mu via Einstein equation. Oh, sorry. Oh, so you give me a question. Sorry, if we apply this to see the metric which if we apply this to see which execution with the new metric save. Oh, you're right. Can you see, David? Oh, can you see? Can you see? Oh, you're right.
Yes, I see, yes.
Okay,
this is my concern about this BMS symmetry and this story. I already asked you, yeah. I'm not sure about the metric which you generated after the super translation. I'm not sure it's still the solution of the Einstein equation or not.
That's a question, and that's a nice, good question. So we use just a coordinate transformation. So the metric is also a solution of Einstein equation. Yes, you're right. Okay. This is a right question for your answer, your question. Okay. If you have another question, please ask me again. Okay. Okay. So
you can send the chat to everyone, I think, in that case.
Okay.
No, you can send the chat to everyone so that everyone knows what you're asking. So
okay.
If you have a problem in network, yes. Okay.
Okay. So anyway, so let me go again. And here, so we just assume Einstein equation, perturbative Einstein equation. So here we have informing matter, and this matter has such an energy moment tensor. This energy moment tensor is a space-time perturbation via Einstein equation. Then we can evaluate the charge value shift by using this H mu. Okay, this is our setup. And this is our main result. So for super translation charge at horizon, so this is the result. For super rotation charge, this is the result. Okay, and I like to stress some points of our result. So in the super rotation charge, can you see the green function of two-dimensional shift T here? So this is two-dimensional shift at the horizon. So this result is very similar to the result of Tofu's black hole S matrix theory. So it may be interesting to consider about that. So he said that we have an event horizon and we have an informing particle. This particle is absorbed by the horizon, and some excitation propagated at the horizon, and this excitation becomes a Hawking particle and emitted again out of the horizon. So during this propagation, so this part can be described as such in a two-dimensional CFT. So I'm not sure. So what's precise relationship of our result and Tofu's result, but it may be interesting to consider about that. This is just a comment. Also here, we have time integration contribution for the charges. So this implies that we have long-term memory effect. So in this sense, black hole remembers what passes through this horizon. So this can be interesting to consider such a holographic principle or information loss problem and so on. So our result is of two products. So unfortunately, we have not enough time to talk about that, but I just mentioned about the two products in our setup. One is non-cloning products of gravitational memories at two linear horizons. The other one is the decoherence paradox of absolute matter and gravitational memory. These two paradoxes are already resolved in our papers. If you have interest in this argument, please see our paper. Okay. So let me summarize this part. So firstly, we concern a finite mass black hole, which has Bekenstein-Hawking entropy, and also this black hole can be thermal. Can be in a thermal equilibrium, the Hawking radiation. The Hawking radiation temperature is given by this. And now we can take a large mass limit near horizon. Then the horizon is mapped in the linear horizon in a Minkowski spacetime. And also we have such an unthermal particles for such a detectors, because this detector is now accelerating uniformly. So this detector can see such an unthermal particle. In this sense, unthermal particle is a remnant of Hawking radiation. So this is very crucial point. And also the microstate at the linear horizon can be interact with such an unthermal particle and in a thermal equilibrium state. Okay. So accelerating block numbered clocks at metric detector observe black hole here in a room, as well as a Hawking unthermal burst. Each metric detector determines different physical reality of spacetime for it. So reality depends on the observable or observers. So this is my message in this talk. So first, we should fix some metric detector. After that, we can have observed asymptotic metrics. So this metric is defined by this metric detector, okay? After that, we can argue microstate of spacetime as a reality for detector. So this reality depends on the detector. So detector dependent concept. So this is a crucial point. So different metric detectors experience a different reality of spacetime. And this may be an interesting point. Okay, this is the second part. So I have 20 minutes?
Yeah, about 20. Yeah, about 20.
Okay.
Yes.
Okay. So next, I'd like to explain another story. So covariant building block approach to asymptotic symmetries at boundaries. So in the ordinary scheme, to find asymptotic symmetries, firstly, we have to choose asymptotic metrics as a triad. If the choice is bad, without luck, we encounter the cases. First, integrability of charges lost. To pass the test, many trials are usually requested. And this is a very, very hard task. Next, we encounter such problems. After passing this hard integrability test, it is noticed that the charge takes zero value in the final result. and this is very pity for us. So we should go back to the start point and we restart our analysis again. So this is a very pity story, okay? So let me give you some example to explain such a hard task in the old standard method. So the choice of asymptotic matrix determines the size of the symmetry. So let us consider a three-dimensional ADS background case. Then, so Brown-Henon already pointed out that if we choose such a for condition or asymptotic metric setup, then we just have time translation, the rotation symmetry. So very small symmetry just realized. But if we choose such a modified for conditions for the metric, then we can enjoy that bilateral symmetry, which has infinite number of symmetries. Okay, so in this sense, the first choice of the asymptotic metric is very crucial. Okay, but so nobody cannot see what kind of for condition is an interesting result. So in this sense, ordinary scheme to find asymptotic symmetry is a very hard task. So at the first time, as the initial stage, we should fix asymptotic form of metric. After that, we should find vector fields preserve the asymptotic form. So this is asymptotic killing vector. After that, check whether the charge is integrable or not. If not, we should go back again and we should change the asymptotic form and we try and try. And after that, if we succeed in this test for integrability, then we calculate the charges explicitly. Then check whether they take the various values for the solution. This means that we have non-singlet representation, but it often happens. So we have zero values all of the charges, or just gauge freedom, or we have nothing, we have empty result. Then we should go back again the start point. So in this sense, this is a very heavy task to analyze the asymptotic symmetries. Okay, so this is two home. So in this sense, many trials required without luck. So we would like to improve this pity situation. So the summary of standard method with heavy task. The first, we set a simple metric form in its sense, and in the second stage, find a simple king vectors. This is also not so easy. And in the third stage, check integrability of charges. And this calculation is very long and boring. And in the final stage, check non-triviality of the representation. And the obtained charge value often vanish and just gauge freedom. But our method is different. So this is a new method. So in the first stage, find vector field algebra generating non-trivial charge deviation. We should not have integrated charge itself. We just use charge deviation, okay, at a background metric. This ensures we have already non-gauge freedom. In the second stage, we compute asymptotic metric form systematically from background metric using coordinate transformation induced by this algebra. So this is a very easy task, okay? So we should not worry about our choice of the asymptotic metric form. So we have already, this should be non-trivial. This should be non-gauge free. This has already non-gauge freedom. Okay. So in the last part, we should check integrability of the charges. Also, this task becomes rather easy in our formulation. So later, let us adopt covariant phase space homologies. So this Einstein-Hilbert-Lagrangian and take a variation. Then we get a presymplectic potential like that. And we have also presymplectic current and presymplectic home like that. Then, so the charge variation for the vector field C is given by this equation. Here, this is the Lie derivative with respect to the vector field. Okay. Now, let us introduce such an anti-symmetric tensor like that. Then, the presymplectic current is computed as following by using this S. Then, so in non-trivial representation, this relation should hold. So this is a charge of the vector field C, and this is just variation with respect to the vector field eta. And if we have non-zero value, so this implies that we have a non-trivial representation. We have a non-singlet representation. This is not gauge freedom. Okay, so we assume first non-triviality of our result. So this is our point. Okay, so and this relation can be this relation can be recasted into this form, and also this is still complicated because this G should be all of the elements of the asymptotic matrix. But so we now just consider near background metric or at background metric. So please substitute here just background metric itself. So this is a very simple equation. We call this Tomitsuka condition. Tomitsuka is my grad student, Takeshi Tomitsuka, and he found this equation. So this guarantees non-trivial values of the charges. So this is a non-singlet. The task of finding asymptotic symmetry becomes much easier. So next, we just make a vector field algebra A from the initial two vectors satisfying Tomitsuka condition. So Tomitsuka condition requires two vectors, eta and xi, and so they satisfied this one. But by using two vectors, we can generate a closed algebra. Okay. First, let's compute such a computation relation of the two vector fields. Then we may have another vector field, but we can check other computation relation like that. Then we can list up all of the vector fields, and they should be make some algebra A. Okay. After that, apply coding transformation generated by this algebra A to background metric. Then we get asymptotic metric form. So this is an example. So if the two vector eta and xi make a closed algebra, so very smallest algebra of A, then so it is very easy to generate such a metric, make a asymptotic metric form like that. Here we have this is a configuration space of metric, and at this point corresponds to the background metric. Then here we have two vector fields, eta and xi, and we can integrate along this line, along this vector field, and we can generate such a set of the metric. Okay, so we regard this as an asymptotic metric in our theory. Okay, after that, we should check free integration condition. So eta xi chi belongs to the algebra A. Then we should check this integrability condition. We often fail to pass the test of this condition for our selected vector fields. In order to pass this integrability test easily, we should first check a simpler test for our vector fields. Just check the integrability as the background metric. So at the one point. So this is a very simple check. Okay. So after that, if our choice of the vector field is bad, we can notice that the fact of the go, we can notice the fact and go back soon the Tomiska condition again. Okay, so before going with this, we can check easily this part. Okay, okay, so this is our approach. In the first stage, we fix a background metric G-bar and find two vector fields satisfying equation 36, this one. This is the Tomitsuka condition. After that, introduce a minimal algebra A and check whether the equation 38 is satisfied, this one. So this is integrability check as the background metric. And after that, the construct a set of metric G mu. After that, in the integrability equation, the whole elements of the asymptotic metric satisfy this one. Okay. After that, we get the charges, calculate the charge by using this. So this is our approach, building block approach. So this part is very easy. This part is also easy, and this part is easy. So compared to the standard method, our building block method is very, very easy. Okay. So let me show you some explicit example. New symmetry at the Lindra horizon.
Okay, 5 minutes notice, just
5 minutes. Sorry. Okay.
Yeah.
So
without including question. Yeah.
Okay. So let's go
more. Yeah.
Okay, so Lindra software here, we consider this is a background metric of Lindra metric, and we consider general form the two vectors, Xi and eta, and we write around the Tomitsuka condition like that. Then we can find such a new symmetry. So V1 and V2, the vector field, and they make a closed algebra. And we can generate such an asymptotic symmetry, asymptotic, and also we get non-zero value of the super dilatation, HV1, HV2. So anyway, this is a non-trivial new symmetries in our formulation. So our building block approach is easy and powerful and provides successful exploration for new asymptotic symmetries at horizons. Our building block approach applicable to other boundaries in the GO. Actually, new result for finite mass black hole horizon and the horizon will be reported in our forthcoming papers. So let me summarize my talk. So stationary black holes actually carry non-vanishing classical charges of super translation, super rotation, and an asymptotic symmetries. General formula of the charge shift to the super translation, the super rotation at linear horizons. So that is infinite mass black hole horizon. This is available now. Possible to resolve two paradox using these using the results. So, and also finally, I just explained the covariant building block approach to asymptotic symmetry at the boundaries. So this provides a superpolarization as a new software symmetry at the linear horizon. Anyway, so thank you very much. This is that's all. Thank you very much.
Okay. Yes, plenty of question time. In fact, 10 minutes we just resolved. Is there anyone? Let me ask you, or maybe comment, half comment and half questions. The software you define through accelerating clock or accelerating observer has some similarity with what I call soft modes, probably same thing. And there you mentioned kind of classical, in a classical regime. Yes. But in heuristic case, if you want to get the classical, this software as much as Bekenstein-Hawking match, you have to put the detector pretty close to the horizon, right?
Yes, you're right.
Yeah. And there, to saturate the Bekenstein-Hawking, you have to go to the regime where the temperature becomes Planck or string, depending on if you count the species or not.
Yeah.
So all the dynamics of these microstates associated with those hairs or something, you cannot describe in a classical or even semi-classical regime. Do you agree?
Yes, you need
Okay.
quantum gravity.
Yes, yes. Okay, yeah, because you mentioned classical, but
okay.
I think if you become quantum, right? I mean, you have to go beyond the regime you can trust.
Okay, yeah, I understand your point, but I stress why we have such a software in the classical regime. So this is some evidence. So we should consider such a symmetry. So
Yes,
if we
yes.
have no such evidence, we have no clue. But,
Exactly. I totally agree. Yes.
Yes,
So,
yes.
in fact, classically, because you don't have any kind of Hawking cloud or Hawking radiation, you can go to as close as you want, right?
Yes.
I mean, to the horizon. So in that
Yes,
sense,
yes.
of course, here is infinitely many here, clearly. And
Yes.
because entropy is, of course, area over G Newton, H
Yes.
bar in the denominator. So if you
Yes.
set the H bar to be 0, of course, entropy
Yes,
is
yes,
infinity.
yes.
So nothing wrong with it. So that's what I meant, like this mass and so on. Classically, you see the hair. That's,
Okay, that's good. But
yeah.
in our result,
Mhm.
we just propose some observation of holographic charge. The charge can be classical, but it's not coincidence with the Hawking-Bekenstein entropy itself. But we have non-zero value in the classical regime. Okay, so by using some condensed matter physics analog of the black hole physics, it may be interesting to evaluate or observe such holographic charges. And so by using such accelerating detectors at the electrons. So it's another story. Anyway, so you're right. So if you consider such a quantum gravity effect, yes, we should take account of that. Okay, I agree with the point.
Okay, that was it. Anything more asking Masahiro? Okay. If not, let's thank him again.
Thank you. Thank you very much.
Great talk. Thanks. So as I said, there was some one cancellation. So the next one is our last speaker of the session.